Hi, good morning, everyone. Yeah, thank you for notifying me that my audio was off and I was waiting for people to join. I'm seeing that still people are joining, but normally I turn on my video at least so that you guys know that we are starting. I put this one here. Yeah, we are building up good momentum, 23 people. So we can get started for today. As usual, so where we are at module number 6, and we are getting familiar with NBCC section 418. And yeah, about good timing, like 21st, we are almost chasing our schedule. Just a reminder that by end of next week, we like to receive the draft report where you should show about 60% progress, 60, 70, whatever, or more if you like. And then me and Behnam will review your work and I will give you comments. We'll provide comments to your work. Then you have 2 more weeks, or maybe, I mean, you can continue your work and maybe in about 1 week, by about July 5th, after your reading break, you will receive some comments and then you will have 1 more week of time to address those comments and finish. And I mean, you will be very happy because by about 12 July plus minus, you are 90%, 80% done with this course, and or maybe we can say 60%, 70% done with this course, and then you can focus on your other tasks or projects or prepare for August vacation. So that's what we have. Generally, Bernard was very happy with the way you guys drafted your work plans. And I had a quick look. They look better than last year. So I think you guys are progressing well so far. Just keep on doing what you are doing, and it would be great for all of us. Finishing in time before August. Yeah, last week I was presenting NBCC 2020, and there is a link here, and you can even Google search it, so it's downloadable. And it's a good decision made a few years ago that they make this like free, available to everyone, because it's generally, I think it's funded by taxpayers, so they shouldn't really charge. Like development of the code, development of the model code, yeah, like probably is some sort of taxpayer money, so it should be free. So you can download that. We talked about the base share, the concept of base share, and why in structural engineering we call it base share, because it's like the total equivalent force that we apply to a structure to mimic earthquake response and earthquake forces and earthquake displacements, so that we can I mean, in a way it's easier, but sometimes it's better because it's easier to do and easier to verify and easier to validate and easier to gain confidence. Sometimes easy procedures are more correct because like a second person and a third person can quickly verify them and make sure that you are in the right direction. In the industry nowadays, like you guys, the younger guys, you like the more sophisticated computer modeling, but sometimes it's more difficult to gain confidence and make sure everything is correct and reasonable. These solutions, the simpler solutions, are easier to verify. So at least I generally recommend, I think we had a lesson about that as well, or part of our discussion here, that at least we should go in multiple steps and start with the easier to understand and easier to verify solutions. And then if there is time and money, interest in client, then as a second step, go to more difficult solutions, which are more accurate in a way. And there is a lot of interest in them nowadays, but at least do a step by step. Easiest solution based on this simple equation and code. Then second step, I did RSA, and this is my model, and the results look different. Because of this reason and this reason, I have reduced the base share, and I think it's because by 10%, and I think that 10% is because I'm using a better solution. And the reader has confidence, okay, there is a very easy to verify solution. Now the solution has improved by 10%, and these are the reasons for that. Then there is more budget. Okay, I did a time history analysis, detailed time history analysis. I reduced the base here by another 5%. And then the reader again says, yeah, makes sense because RSA is normally conservative. And they have done this company, this consulting, my colleague in the company has done a good job going to next level of sophistication, and he has saved the contractor or the owner some money by reducing the base share, which is very nice. So these are very valuable solutions, and they are based on like lots of research and experience and experiment by engineers. So we discussed the parameters involved. Again, based on an earthquake engineer's judgment, the next sense. I know that was quick, but we gave you a high-level introduction to earthquake engineering. So you know that like a spectral acceleration multiplied by mass is the force that you expect to see. However, you are doing a single mode calculation versus higher mode calculation, and therefore you need an adjustment for that. There is a importance factor because the more important structures will be less tolerant, say for if you want to think extreme, we are less tolerant towards cracks in a nuclear power plant versus a building. I mean, the building won't collapse because of the crack, but nuclear power plant, maybe a crack will cause a lot of hazard to the people around it. Therefore, there are importance factors. Just to build these ideas into your engineering judgment. Why? I mean, without looking at this equation, you might say, "Oh, I'm designing a major bridge. Maybe there should be a factor that increases the demand. Maybe I should build it stronger." And then you go back to your book and see that there is the importance factor. And however, if you start designing using this part, you will end up with hefty sections and impossible build sections. And therefore, you should also build this idea into your engineering consciousness that while a lot of the calculations and analysis that we do is based on elastic assumptions, which is this side, practically there is a lot of energy absorption because of ductility, and we try very hard to create ductile buildings. Therefore, there is a reduction factor, which is a result of ductility, like the first R, RD. And there is another reduction factor because if you follow up your everyday calculation or course calculations in design, there is a lot of redundancy and overstrength gradually build up one by one, which they add up, and you can take advantage of this fact and the code, use the code values, not your own judgment, but then have that sense that we are gradually building up more and more overstrength, and we need to maybe scale it back. And that's where the overstrength factor comes in. That overstrength factor is also very important when we think about protecting the non-ductile members. That's another place that I think we already slightly discussed that, but we go over that one more time. That overstrength is also important there to protect the non-ductile members that we are designing. Again, philosophy of ductility and why after a elastic calculation of base shear, we should reduce the force for design, because elastic easy solution is like this line and gives you this movement versus displacement. The displacement is agreeable because it's like, I mean, you can deform a structure as far as you want, but starting from some point, the structure will not really pick up load. Therefore, you should be, again, build up in your judgment as a structural earthquake engineer that if I have completed elastic calculation, I'm going too far in my forces, and let's look at my code to see if there is any excuse to reduce that load. And there is an excuse, the code has already thought about it, and it gives you the reduction factor based on ductility. Going next step. So ductility related, we discussed that the structure as a members are ductile, but then because of member ductility, the whole structure is ductile. And this has been an exercise in envisioning the ductility of this whole system with many members and many connections. Pushover analysis was performed. Pushover analysis helps us, that's a benefit of it, that helps us with like ensuring ductility, even if you, like, what I'm trying to say is that like you can get into numbers, like draw this plot and get exact numbers on how your structure will behave, deflection versus force. But then, even if you are not exactly chasing these numbers, when you see that your structure gradually gives in to force, you become more confident that you are really designing a ductile structure. But if you see that this line is remaining straight, you should get worried that maybe you are not providing enough ductility in the system, and there's no energy absorption in the system. So building up, even just doing a quick exercise in building up this curve, here will give you a quick sense of confidence that you are providing ductility. And then second to that, maybe you can measure that ductility and make decisions on the level of activity in the system. So there's ductility in the system, so we can, or the code can provide a reduction for ductility, because your typical linear calculation or linear analysis will give you a much, like continuing this linear line, you will end up with a much higher force than this structure can even take. So the forces are definitely lower. Building up that fact within your judgment as a structural earthquake engineer. Now, here we try to basically build up in that sense that into your engineering judgment that structures, for many reasons, we over-design them, and a lot of time we are happy with that. We prefer a structure to be too strong rather than too weak. there are some phenomenal part of our analysis steps, quite a few of them, help with building up more and more over strength. One is like factor strength, because we use a reduced strength in LRFD method. It's like load and resistance factor method. We increase the load and reduce the resistance. So the resistance that we use for design is less than the minimum strength. So the codes provide minimum strength, and we even reduce the minimum strength into a smaller number. However, minimum strength is smaller than probable strength, because if you, like, somebody is doing tests on the steel, you will never do that, but I mean, we trust what the numbers that we receive from the vendor. But if we do a test and say get the average of the tests, our strength would be at this higher level. However, the process in ASTM or the CSA is not to recommend the average, but to recommend a measure of minimum, like 10 percentile or 5 percentile. So even the minimum is less than average. The minimum strength recommended by the code or the vendor is smaller than the average value, which we can call it probable strength. And probable strength is when the material starts yielding. Even when the material starts yielding doesn't mean collapse. It means for most material, even steel, it means the material or the member will take on more force up to the maximum strength, and it will collapse. So you see here that even in determining the material strength, we have been too conservative, or not too conservative. We have been conservative in a good way, with a positive tone, but there are several conservativeness built in. Then we use this smallest value shown here as VD prime to design, and we come up with a, say, profile size, but then we go, like, we pick a profile which is slightly bigger. Then another reason to think that there is overstrength in the system. So that's a backbone or the idea behind overstrength factor. But again, I mean, don't use your own calculation. The code tells you that based on experiment and test and experience, how much overstrength is built into any type of structure. Last week we opened the code. Yeah, so I mean, hopefully you guys have already downloaded the code and you can find your way through it, at least through the earthquake load section. And yeah, I mean, they keep on moving things around a little bit. So sometimes you are familiar with one version, next version is slightly different, but the concept almost remains the same. The code gives you different both reduction factors, which they call it modification factor, but they are really there to reduce the demand. That both the reduction factor resulted from ductility and reduction factor resulted from overstrength. What the code knows based on experiment and experience and engineering judgment, how much reduction is within each structure. And there are recommendations on how to make each structure more ductile. Maybe I think clearly said in the new, like, say, steel code we have opened like this part of this table, which is about the steel. So the steel code clearly tells you how to make sure your structure is considered, how to detail the steel structure so that it's completely ductile or moderately ductile. And if you don't do anything conventional, it remains with limited ductility. So that's like price that you pay is that you do more detailing, and the advantage you gain is that you deal with a smaller earthquake, because remember that this is really reduction. Your earthquake force is divided by this value. So sometimes you have to do, it's again some sort of cost benefit calculation in a way. It's okay, do I need, if you are a decision maker, you say, do I need to pay good consulting this amount of money so that my profiles are smaller, or say maybe it's cheap, consulting is expensive, then larger profiles, but I pay less to consulting. However, there are some restrictions here. The restrictions here are for different seismic categories. We briefly introduce seismic categories to you. Seismic category, I think this is new to NBCC. US code ASD 7 was working based on seismic categories for a long time. I think it is new to 2020 NBCC that they aligned themselves and now they work based on seismic categories, which inside it has the importance of the structure slightly and the region of the structure, PGA in the region, and also the importance of the structure. So you see in this table, NL means no limit. Here, say, in any seismic category, high seismic category, you can use ductile steel structures, which are like the best in terms of ductility. There's no limit in height. However, like in contrast, when you do conventional building, when you think that, okay, I put very large profiles, I spend more on material, but I go conventional, the code strongly says, you are not allowed to create any building taller than 60 meters if you are seismic category 3. You are not allowed to design any buildings taller than 30 meters if you are seismic category 4. So I generally suggest that, if somebody is speaking, I very strongly suggest that you, like at your even spare time. These days, everything is PDF. Your cell phone, larger screen cell phone, browse through that chapter of NBCC and try to find your way. People like me, even now, you just find our way. It's not like I memorized every corner of it, but I can navigate my way. And if a question arises, then I can find the corresponding table, etc. That is necessary for a quick engineer, but some people are too smart and they just know it in their memory, which is also good. And the concept of capacity design is super important. If a good earthquake engineer should somehow, at least, I try to understand this. Every time I understand it better, I think that I teach it or when I discuss it. But it's very, very important concept in earthquake engineering. If you understand it well, you are a great earthquake engineer. And the idea, as we said last week, was that we provide ductility in our system through certain parts of the system. Like, the system is a structure for us. We are structural engineers. It's not that every member of the structure is needed to be ductile. However, certain members we want them to be ductile. There's a concept of load path that any structural engineer, even non-earthquake structural engineer, should really be fluent with. That we always talk about load path, how loads are carried from a location in the structure to foundation. So that's the purpose of building structures, is to carry the loads into the foundation. So that the right-hand side is your foundation, left-hand side is where the load is originated. In our case, earthquake engineering, the loads come from masses and weights in every floor of the building. So you have the loads, the earthquake loads coming from masses, originated in the mass, they are a result of having mass. So every mass, every floor, most of the mass is concentrated, or we can assume that it's concentrated in the slabs or in the floors. And so we have a load path to carry our loads in the slabs all the way to the foundation. This part of the load, a lot of it, or most of it, remain brittle. We cannot make everything ductile, but we want to, at least to reduce the level of the load, we need to provide ductility as part of the load path. So although schematically, say 60%, 70% of this path is non-ductile, but there is a ductile member in between. And that is very key in earthquake design and ductility. Now the intention of earthquake engineer, a structural engineer who is expert in, as you guys will become, expert in earthquake, is that they want to have this ductile member active during earthquake so that this ductile member elongate and dissipate energy. And at the same time, because these members are brittle and they may cause serious collapse or failure, we want to protect them. We don't want them to elongate or crack or anything. That's where the concept of capacity design came in, that the intention is to protect these brittle members, which are inevitable, and concentrate all the deformation and dissipation within the ductile link, because we trust that the ductile link elongates and dissipates energy without failure, without collapse, without dangerous collapse. So I think that's a very, very big part of philosophy, we call it, or science of earthquake engineering design when it comes to the structure. So we stopped last week. We stopped at about this point. I was trying to more like the previous one is more schematic. It's very schematic. It's good to have this picture in your mind as a good engineer. But then we are a structural engineer, so let's look at building, typical building, 5-story, and see how the interpretation is in the structure. And how the capacity design is compared with what they call the direct design, which is what you do. So you design the building for wind, or even lateral wind, or vertical loads, live load, and people and equipment and cars and whatnot. That probably you have taken courses for that. Let's see how these two concepts compare with each other. So there is an analysis part in a way, which remain the same for load concepts. You apply every load and say lateral load in conventional, in direct design, maybe it's wind, but in earthquake design, it's earthquake plus wind maybe, or We normally don't combine them. Maybe in exceptional cases we combine, but normally we don't assume that a strong wind happens at the same time as a strong earthquake. Maybe there are special circumstances, but most of the time we don't combine them. So you define all the loads, and you know that you make certain that the connectivities are there and the load paths are defined well. So both vertical and lateral load go all the way to foundation. Now you perform analysis, which, as everything else, could be more sophisticated computer model or back of envelope simplified calculation. And you come up with the internal forces which are used in the design. So this step remains the same. And so in order to add here we will repeat this a few times, that building the high-level concept or general concept is to have the beams take on the role of ductility and have the columns to remain more strong. I mean, it again goes with the engineering judgment that we say, okay, there's heavy loads on the building, and we don't want to take any chances that the building will collapse. So we prefer that the plastic hinges occur in the beams, because it feels more safe that the other columns remain really strong. So this is based on good engineering judgment. In most of the cases, we would recommend for building a structure to have ductility within the beams, and therefore the column is part of the brittle ring. And most of the time, the connections are also considered brittle. It's difficult to make connections ductile enough, although we always advocate for more ductility in connections, but connections are limited, so they cannot really elongate in any direction. So that's again general judgment that connections are also on the brittle side. Now we come here. If your load is wind, say everything of the scenario remains the same, but this lateral load is caused by wind, we go more towards the direct design philosophy on the left-hand side, which means that we just simply read the forces from, say, sub 2000, tells us what are the reactions, end reactions. The end reactions in the beam help with design of the beam. The end reactions in the column help with the design of the columns. And the corresponding connections also designed accordingly. However, when we are more in the design of earthquake, especially non-conventional, more ductile, where we can take advantage of ductility reduction ratio, the reduction ratio caused by ductility, we should think in terms of capacity design. Then the steps are something like this. I mean, we will reiterate this a few times. You have NB for your ductile beam member. You design your ductile beam member for NB. However, practically, the capacity of your beam member that you have designed, because of our strength issues that we just talked about, the capacity of that beam is higher, maybe sometimes even twice higher than I can imagine that scenario, that the ductility of this beam member is twice higher than what the analysis told us. So the ductile member is very strong. And in a way, we want to protect the non-ductile members against that strength. Therefore, we push up the demand on the non-ductile members, and practically we push up the forces in connection and in columns based on a prime B max, which is greater than NB. And prime B max pushes up the forces in the columns and connections and brittle parts. So that's a concept. This concept, always you can have it in your mind. And then when we come into structural engineering, more focus on structural engineering, we end up with this scenario that the ductile member capacity is used in the design of the non-ductile members. So let's see how the ductile yielding mechanisms are in different scenarios that we encounter. Left-hand side is a concrete shear wall or bridge pier. We said that we don't like plastic hinges in vertical members, but in this case, as it's inevitable, plastic hinge might happen at the base. We try to really avoid higher elevation than base, but in the base, like if everything is yielding, base is also under a lot of stress, and maybe there is plastic hinge in the base in buildings. In bridges, even the philosophy is different, so we don't get into that. In bridges sometimes reverse, like plastic piers and non-plastic superstructure. But then, yeah, that's the mechanism of the development of plastic hinge in a pier or in a shear wall, which is almost similar. The coupling beams deform elastically in shear and flexure for this building. We said that we like to see that. We don't like to see as much, like it less, if I can say that, to see plastic hinge in columns, but at the base sometimes happens. So that's a building design philosophy. But just sharing what plastic ductility means in this type of structures. In reinforced concrete two-column bridge band, what does it mean? The plastic hinges might happen at the bottom of the piers of the band and at the top of the piers of the band. So schematically, two plastic hinges on two sides. Plastic hinge, you can imagine too much rotation, the concrete is giving in to deformation and it still is yielding, etc. So that's what it means in the concrete members. The side on the right side, we have a building, like a structural building. And yeah, so we advocate plastic hinges in the beams. We don't mind at the base, but we really try to prohibit having too many plastic hinges on the vertical load carrying side. Again, what it means physically in a reinforced concrete moment resisting frame, it means that lots of cracks is happening there, and steel is yielding. And on the opposite side, the concrete is under a lot of compressive stress. Schematically, we say plastic hinges are happening. We next see what we mean by ductile yielding in steel concentrically braced frames. We will reintroduce this one more time when we are talking about the steel. Concentrically braced means that the two braces are meeting each other at one point, versus eccentric bracing, which means the two braces are not really meeting each other at one point, and there is a shear region at the in between. So the mechanism, the ductility mechanism between the two is slightly different, or completely different. In the concentrically braced frames, we are mostly depending on the braces themselves to provide ductility. As you see here, some ductility is provided, which means energy absorption is provided by this brace extending too much and yielding. Some more ductility is provided by this other member buckling out, compressed, buckled out, and when they are buckling out, basically some plastic hinges happen. They see a lot of moment, larger moment than they are designed for, and therefore the process of buckling and creating those plastic hinges help with energy absorption. So it's beneficial in terms of energy absorption. And so in this particular system, normally when we design bracing, we mean that there is no moment resisting in the columns and there is not much plastic hinges development, but there are mixed design as well. Maybe we can almost imagine mixed design where we are both dependent on moment resisting frame and concentric bracing. In this system, we have additional energy absorption through creation of plastic hinges. Or maybe in this picture, I think it looks like the picture is emphasizing that this was originally pinned. So maybe the no energy absorption really happened here. As I said, this system was pin to start with. So no plastic hinges happened here, but plastic hinge happened here in the midpoint of the compressive brace. But there are also mixed systems where plastic hinge happen both at the beam end and also at the brace. In terms of ductility, I think the code or the experience and experiment suggests that this system on the right does a better job in absorbing energy. And this system that has been probably never considered new maybe a few decades ago, but now they are more and more popular, is basically you put the bracing in, but with a distance in between. And this small distance here, if you model it in your STAP 2000, even elastically, and you look at the reactions, you put a lateral force here. Maybe it's a good exercise that you can do by hand calculation or in STAP 2000. You create this very simple and quick model. One time you do this one, you make them concentric. One time you distance them and make it eccentric. And you compare the results and you see that this arrangement has resulted in substantiated shear force here. So you will see a peak in shear force here. Some smart people decided to take advantage of this fact, and they suggested this type of bracing for earthquake design. And basically, huge shear here might result in yielding and dissipation of energy, and therefore this system provides very good ductility and larger reduction factor based on ductility. So there's a very good system in terms of dissipating energy during earthquake. One more time, reviewing the capacity design procedure. On the left-hand side is a structure, and you might be designing this structure has a roof diaphragm, which would be the main source of your force. Maybe we can imagine it on the left-hand side of the chain here. And then there is a load pad for carrying this force to the foundation, going through the bracing system. Bracing system has created ductility in the system. Like we want to enforce ductility as part of our design. It doesn't naturally do that. It should be designed for that. We want to design this bracing system both to resist the lateral force, prevent collapse in earthquake, and also we want them to act as ductile members. That X bracing, which is concentric bracing. So again, we imagine what we want in terms of this chain, which is, I think, it's a very good schematic tool. The load is on top. The load path goes through the roof diaphragm. So it's important. The roof diaphragm should be designed properly so that the load is carried into the bracing member, the lateral load. Vertical load path is different. It goes through the columns. The lateral load makes its way into bracing. There are certain details that you should be careful with. And then the bracing will carry this load to, there is some dependency on columns and beams, or maybe we want to completely avoid loads going through columns and beams. But some of the load will go through the columns and beams, but we want mostly to go through the bracing to this bottom connection and into foundation. So there are anchor rods and there is foundation. So we should have a good imagination of our load path for this particular load, which is earthquake. And we should know which members we depend on to provide ductility. Here it's the bracing member, and which members we don't really want to depend on for ductility, which are roof diaphragms, columns and beams, foundations, and the corresponding connections, collector elements, which take the load from roof to the beams and also to the bracing and then bracing connection and then the very base anchor rods. These are other non-ductile members. And in terms of capacity design, we want to protect the non-ductile members from sudden fracture or collapse during earthquake. We want only the bracing members to sustain deformation, major deformation, because we designed them for that purpose. So step one is to understand the load path. Step two, like focusing on one of the bracing members and its corresponding load. Bracing members are selected to satisfy, number one, strain requirements under applicable building code load combination. Number two, detailing requirements to achieve ductile inelastic cyclic response. So there's a load combination here, based on the good judgment. The division of work in this case is simple. All the verticals go to column, all the laterals will go to the bracing. So although there is a combination of the load really applied, but we know that lateral will be taken by bracing and vertical by the column. But in general, that might not be the case. Like maybe the brittle is also the ductile. The ductile member is also taking part of the vertical load as well. And then there's detailing requirement. So this member at the end of step number 1, the bracing is fully designed for VF. Detailing requirements should have been met, meaning that like in the still code, there are requirements about connecting the bracing to the system to make sure that it can really sustain it can become ductile when it's sustaining the lateral load. So almost the design of, sometimes it's counterintuitive, like although we are taking advantage of ductility of the brace, appears that the design of the brace is done more conventionally, and it's the other members that we protect. So design of this is done just under applicable building code. So just design this member and then be worried about the other members which are not ductile. Then we go to step number 3. Anticipated inelastic response scenarios are identified. So scenario number 1, where the member in tension, I think the picture intended to say the member in tension in this scenario is becoming nonlinear. Or scenario number 2, where the member in compression buckles out and becomes nonlinear, maybe with 2 plastic hinges or maybe with 1 plastic hinges, depending on the connection. Number 2, probable force demand imposed by bracing members is determined from known inelastic behavior. So basically, pretend that it's too sophisticated, but it mostly comes from the code. But then shows the philosophy behind it. Summary, we are trying to estimate the load caused by yielding of the member, the real member, which might be stronger than minimum requirement. Maybe suddenly the designer decides to put a member here, which is when they are completing step number 1, because of many reasons, like availability of the member, imagine that the minimum member is not available, so you put a member is there, which is for different reasons, economy, pricing, etc. You are putting in a member which is twice as much as what step number 1 really requires. So you have real overstrength issue here. And in step number, part 2 of step 3, we want to estimate the real capacity of that member based on the knowledge we have about how the members buckle in compression, how much is the maximum force they show in buckling of that real member, of that twice as a strong member, how much force does it show when it buckles? That twice a strong member, how much tension does it show when it yields? And the code helps us with finding these values. And now we use the real strength of the member that is really designed there to estimate every other force. So basically, we apply the capacities to the bracing, and now we read the forces that are resulted from that in connections, most importantly connections, and maybe in other members as well. So that's where step 3 is. Other seismic force resisting system components are designed to satisfy strength, not demand. To satisfy strength requirements corresponding to brace imposed loads plus gravity load. And in this case, I think these connections connections on all four corners of the bracing are the important ones, that they should be designed for capacity of the braces, and also the anchors put to carry the load to foundation. They also must correspond to the capacity of bracing, not to the demand in the bracing. So if somehow high level you understand these three steps and these schematics, you are next level, high level capacity designer. Not everybody is there. So this is super important concepts and very, very smart concept, I would say. Now let's get back to the design spectral accelerations. What is the, so just switching the subject to another important subject. And let's join the meeting. Just getting out of this, as I said, it is very important. You will be very famous if you have good capacity design. You fully understand capacity design. I'm not saying that it's easy or anything, but consider it very nice and niche, and people will fully understand it at the higher hand in consulting for earthquake. Yeah, so just changing subject. Let's go back to our SA, spectral accelerations, and the factors that are important in that sense. So that was like we were talking about activity and reduction factors, etc. Now change subject to SA and the factors that are affecting SA. The code talks about site classification. All codes talk about site classification, which is a function of the type of material on the site and its depth. So basically, this is a fillet. Okay, so we are normally interested in the top 100 feet layer of the soil that we are working with, or top 30 meter, because this is feet. We want to geotechnical engineer or site studies give us an approximation of top 30 meter or top 100 feet, if I'm reading this correctly. So there is a lot of variation in the top 40 feet, and we think that 60 feet underneath it remains the same bedrock. So this picture gives us a picture of this site that we are interested in. Yeah, so the top 100 feet, there is a medium stiff clay with certain spec that geotechs understand it better. There's a layer of sand, again, some specs that geotechs know better, and the bedrock, which we say it's almost the outcrop, like the earthquake remains the same here, but softer layers, the earthquake characteristics change a lot. And that's why the code discusses the site class. Will be obtained either from established regional soil maps or provided from a geotechnical report for the site. May vary for large sites, indicating that if you have a large site, maybe on one corner of the site, you have a different profile than another corner of the site. Can be determined using the standard penetration test. So that's, I don't know, geotechnical jargon. It's called geotechnical jargon, but the code indicates that as well. It's important for us to be aware of the top 30 meter. That's what they call it. In the US code, they call it VS30 because that number 30 meter is important. Although they say 100 feet, but again, they call it VS30. It's like this is the shear wave velocity in the top 30 meter is a very important factor in determining the superficial earthquake. Going to the next slide. Site designation versus site class. Conceptually, they are the same, but again, jargons, but almost the same concept. Shear wave velocity on the top 30 meter is very important, reiterating that. And the important factor really physically is the speed of shear waves in that 30 meter. And the very geotechnical people do that. They do seismic measurements in boreholes, they do material study, they do standard penetration test, SPT, but they come up with some value of the shear wave velocity. More recent techniques by taking surface measurements have made it possible to obtain VS30 in a much simpler way and potentially take more measurements across the site. They're like other tests, boreholes or SPT could be expensive, but superficial vibration tests give us a lot of good information at lower cost. We get better information, we make better decisions. And then there are tables in the code that tell you what site designation versus what ground profile characteristics. A lot of times, at least in my field of work, we think and talk in terms of the shear wave velocity, but geotechs will maybe think or talk in terms of SPT results or plasticity index, moisture content, other stuff. But we think a lot about in terms of the shear wave velocity, and this they have like correspond to each other, they correlate to each other. We like the shear wave velocity be higher. That's a benefit. Higher shear wave velocity means that it's stiffer. The material is stiffer. You are more on the rock side. And the site designation, again, in terms of NBC, that site designation term is something new, I think, comparing with 2015. So we're going to, like previously we had site class, now somehow they're going to steps, the site designation and the site class. But in most codes in the world, the site class is definitely important. So for some reason, they have decided to do it in 2 steps. Talk about site designation and then go to site class. Very stiff rock, they call it designation X760. This is speed between 140 and 760 meter per second. They call it designation E. And then, however, there are 2 subcategories for this speed, depending on the profile. It could be E or F designation. And when it's very soft and only by like measuring the speed, the like poor quality, like F means quality, you will see it in the class. And lower speed of shear wave also means low quality of soil. This is like, but for generations, engineers are familiar with like classes, A, B, C, D, E, F. Then you could try to correlate it with designation. Basically, site class A is hard rock, very strong and competent rock. When you move gradually down the ladder from A to F, you end up with like very soft soil, which is not reliable. And when you get to F, normally means that you need serious geotechnical investigation and serious involvement of geotechnical engineer. So going from hard rock to dense soil, soft soil, steep soil and soft soil, and then the bad soil or poor soil. What it means in terms of the speed of the shear wave in the top 30 meters, greater than 1500, down to 760, and down to 360. That's more like measurement, but I deal with the speed of shear wave versus side class. What it means in terms of SPT, more geotechnical nomenclature, but maybe you can receive reports in terms of SPT, and then you should decide about your site class. And what it means in terms of average undrained shear strength. Again, no, geotechnical issue, but you may receive these values and you can correlate the site class. For softer soils, there is more descriptions. Soft soil is any ground profile other than site class F. So that's first read site class F. Bad soil is any ground profile that contains liquefiable soil. So if there's potential for liquefaction, it's like huge red flag, and just call your geotechnical engineer, don't accept responsibility. And yeah, so liquefiable soil is very bad. Like, but then sometimes we have to deal with it. So we should collaborate with the geotech, peat, or highly plastic, or medium stiff clay. Those are red flags. Poor material, where we need like serious collaboration with the geotechnical engineer. And then, other than that, if it's not under category F, then we look at category E, and high plasticity index or moisture content, which is high, or shear strength, which is low. Those are indications of site class E, which is concerning, but not as bad as F. F is just bad for us. Be very concerned and red flag it, and avoid it, etc. Now, design spectrum, we discussed it previously in the context of spectral analysis. But here we want to get the design spectrum, meaning what the code recommended for design. And in the new formulation, in 2020 formulation, you will see that a lot of times in the books or in my presentation, we only talk about SA of T, and then we say it's related to the site class, but new nomenclature, they have called it SAT and also designation. So emphasizing a lot that designation is important. Just don't use SAT naively, pay attention to the designation. It's a 5% damped spectral acceleration expressed as a ratio to gravitational acceleration. So this is a ratio to gravitational acceleration. For people who took dynamics, you know that like acceleration multiplied by mass is force. But then because this acceleration is basically calibrated with respect to gravitational acceleration, it's divided by g. Therefore, we can more easily multiply by weight. So that's a comment for people who are more familiar with dynamics, general dynamics, that why it appears that we are multiplying acceleration by weight because it's already divided by g. At the period t, which is period of interest normally for us, like what is the primary period of my structure, emphasizing more that the site designation is important in this decision. Don't forget the site designation. Don't use them naively. Pay attention to the site. And could be obtained from an CAN website. I tested it last year for the first time. So in the previous versions of NBCC, or what we were doing for maybe long time, even that was long time for 20 years or something, normally the site provided a raw spectral acceleration, and then we did modifications ourselves to account for site designation. In the new format, we may try to do an exercise next time. The site do the calculation for site classification as well. So you insert the value for your site class as well. The outcome is better because it's already accounted for site classification. Previously, or even maybe now in US code, you should also pull out the modification factors for site class, but they have made a wise decision to include that in their little calculator. Site designation determined from soil report. So you read the soil report and decide about the designation. Yeah, so just I think I added this last time that lots of time we don't do any of this. Geotext will do it to the end, but we should double check. We are in charge, so we should double check, make sure that they have done the right thing and provided the correct spectrum acceleration. Response spectrum is a plot of peak responses. We said that a few times. The design spectrum is provided by the code at specific representative values, and we interpolate between them from short to long periods. Yeah, so we will go through using the latest website next time, next Tuesday. Hopefully you joined today's presentation. In the next couple of minutes, if you have questions, let me know. Otherwise, I hope everyone has an excellent weekend and keep on working on your project. That's a very good learning tool. And this project, this course, I think it's already assigned. I recommended that. It's assigned it's categorized as a design course. So it's very good that you do a project and deal with real world problems rather than going through some equations. So we want that. And I said that this course could be a design course. Thanks a lot. Take care. We will talk next Tuesday, and I'm waiting for one or 2 minutes for any question.